Well, your info is about 4 years out of date, mind you. I do not work for that company anymore. They aren't called that anymore. And I don't think I've ever thought about writing an operating system. I think you might mean programming languages, though I never actually got around to writing those either. But it's been fun to try. But they got one thing right. I've been doing Rust recently, and I've ended up working on this library for Rust that provides persistent data structures, which is something. I mean, Rust has pretty much everything now. If you just saw the previous talk, it's got like web frameworks and everything. What it didn't have, interestingly, was a good story on data structures other than like the normal mutable, simple data structures that are in the standard library. So that's what I've been doing for fun recently, essentially. I'm not going to talk a lot about Rust. I'm going to talk about why you want persistent data structures, and I'm going to talk quite a lot about how they work. I'm going to go through a couple of the simpler ones in some detail, and then I'm going to give you sort of an overview of the more recent developments. The definitely more complicated, but quite improved data structures that we're actually using nowadays. I'm going to try and leave a lot of time for Q&A. If you want me to go into details about the Rust implementation, I definitely will, if you ask for it. And if you want me to go into more detail about the data structures, I'll totally do that too, if I can. But for now, I'm just going to basically go all fangirl about how awesome persistent data structures are for about half an hour. So, first of all, this is Don. Don is going to be your background for today. You might have heard of him. He's written a couple of rather popular books about programming. He was maybe like the first person who wrote serious literature about data structures, for one thing. But I don't believe he touched upon persistent data structures. That wasn't really a thing at the time. He's also written this typesetting system that everybody hates and everybody still has to use. Anyway, Don wants you to learn this, and if you're starting to feel like I'm going into scary territory, just remember Don is right there behind the text, and he's cheering you on. So let's start with the most fundamental question. What is a data structure? Anybody got a good definition? Oh, come on. No? OK. So I basically did what everybody would do in this situation. I asked Google. And it says a data structure is a way of organizing data so that it can be accessed and modified efficiently. That's, well, yeah. Examples would be lists and key value stores and a couple of other things that you don't generally see as much in like the standard library things like graphs and maybe matrices. But I think mostly data structures that you end up using a lot tend to look like either something list-like or something that maps a key to a value that you can look up. Or a combination of both, like sets. So what is the most basic, the most fundamentally simple data structure that you can imagine? 5-letter word. Starts with an A. Arrays. Very good. So this is my diagram of what an array might look like. This is an array of 6 elements. It's basically just a pre-allocated chunk of memory with the right size to fit 6 elements of whatever type. Let's just assume they're bytes and for this example. So this would be like 6 bytes of contiguous memory that you just put your stuff in. That's about as simple as it gets. Lookup is really fast and everything else is really slow. But what are persistent data structures? So a persistent data structure is a data structure that essentially preserves the previous version of itself when you modify it, which means that you can make changes to it, but you will get a new data structure in return when you call the change function. You won't actually modify the thing that you already had. How would you, out of interest, how would you do that to an array? How would you make an array a persistent data structure? You copy it. Yes. Now, that's not very efficient at all, but it works. But this begs the question, though, why would you want a persistent data structure? And there are the usual arguments, like reasoning about your program, like proving correctness and theorem provers and blah, blah, blah. And like code is essentially mathematics, and you should be able to prove that your program works. And persistent data structures make reasoning about it a lot more straightforward. But basically, what this boils down to is that when you call a function, if the only change that actually happens when you call a function is that you get something new back out of the function. That's just a lot simpler to keep track of than if you call a function that will like hit the file system, read a file, write something back, and maybe call an external server and then return you a result. This isn't really, I mean, this is a really compelling argument if you're a mathematician, though. But I think to the working programmer, this argument sort of falls flat. It's not really obvious that this provides a lot of benefit. I mean, mostly we're programming for situations where everything is a mess anyway, and a bit more of a mess doesn't really matter. So I'd like to present a couple of other reasons. Clicker still works good. What we've been seeing recently is this idea that state is something that evolves over the lifetime of your application. And this is where persistent data structures come in handy. For starters, we got recursive algorithms. Basically, like say, brute force searches. I think my favorite example might be a Sudoku solver, a stupid one that will just brute force its way through the answer. So basically what you would do then is you would have the Sudoku board as a data structure. An array would do fine of 81 bytes. And basically you just start at the first empty cell. You put the first available number in, 1, and then you recurse down the entire rest of the data structure, basically proposing new numbers as you go. And the recursion goes quite deep. And basically, you're going to run into a lot of dead ends. And when you backtrack, if you're not using persistent data structures, you're going to have to make sure that you sort of restore the previous contents of the data structure when you go back to the last known good state. Wish I could have shown you some code for this, actually, but I'm not actually going to dwell on this. A much more exciting example is stateful applications, and in particular, user interfaces. This is a huge thing in web development and such nowadays. You've got things like Redux and Elm and the Elm architecture, where basically your entire state, there's a single source of truth, as they call it, for your entire application state, and that tends to be a persistent data structure. Although in Redux, it's actually done the stupid way, sort of. Your state tends to be a plain JavaScript object, and you use it as a persistent data structure, which means you have to copy the entire state every time something happens in your application. And this is, let's see if I can do this, because I want to show you this application, this Sudoku game, speaking of which. Oh, this is going to be tricky. So this is written using Redux. I can't see my screen down there. And no, this isn't it. OK, I'm going to go over and look. Ah. So basically, does that say Redux? That says Redux. That's the Redux console. So basically now the state of the Sudoku board is a persistent data structure. And Redux manages the current state of the application, and the Redux dev tools actually stores the history of my application. So I can go I can start playing this game very stupidly, but just sort of filling in numbers as we go. And you'll notice that the Redux dev tools actually record my changes here. And every item in this list is a full state, which means there's supposed to be a scroll bar somewhere. I wish I could actually see this. Which one is it? I'm just going to press buttons until I find it. Bear with me. This isn't working at all, is it? Where have you gone? I know you're there. Oh, wow. Very radical things are happening on the other screen here. Well, then can I? This falls flat, doesn't it? Well, I mean, I can see these. Whoa, totally not. This is annoying. It was working so well earlier today. But that's how it... Oh, no, I got it. That's it. There's my slider. So basically what I can do now is I can scroll through the entire history of the application. And you'll notice that the application actually restores its previous state as I move back and forth. Then I can go back to where I was. I can just sort of scroll back and forth through the entire state of the application. Now, this is not a very smart data structure I'm using. It's literally just copying a JavaScript object. And with something the size of a Sudoku game, that's not a big deal. You can play this game for a very long time, and you're probably not going to run out of memory. But for a more complicated application, this might start to get problematic. But I'm going to get back to that. Now, let's see if I can close this without closing my slides. Yay. OK. That was argument one that I think might be actually meaningful to your working programmer. The other one, if my clicker still works, it totally did. Just on the wrong screen. OK. The other one is thread safety. And the lovely thing about persistent data structures is they don't ever change once you've got them. So that means basically you don't have to worry about thread safety at all. You don't need to care about locking a value that is never ever going to change again. But I was mentioning memory usage because in my Sudoku game, basically what I was doing is I was copying the state, making an entire fresh copy of the state every time something happens in the game. And that's sort of a bit wasteful of memory, especially if you've got large data structures. And in addition, if I actually have to copy my state all the time, that's going to take some CPU time as well, isn't it? And that tends to be the thing that makes people worry about whether persistent data structures are actually a good idea. Is it going to be really expensive? So this is where I get an excuse to actually talk about how persistent data structures are implemented. Now, I got you the absolute simplest persistent data structure that I could think of. Anyone care to guess what's coming next? Lispers in the audience?
Linked list.
linked list, in particular, single linked list, the cons list. This is a very, very old data structure from back in the 50s. It's basically this idea that you got a consel. A consel is basically just an array of two items. The first item, assuming it's a proper list, in Lisp you could use both items as any value, but if it's a list, the first item will be the element, and the second item will be a pointer to the next consel in the list. So basically, it's a very unbalanced binary tree, in a sense. I mentioned this goes back a bit. This is my favorite part about consels. So the whole thing is called a consel, which is cons is short for construct, and so far it all makes a lot of sense. The left-hand element is called the car, and the right-hand element is called the cudder. Are you still following? Now, this means contents of address register and contents of decrement register. And the reason it's called that is because that's literally where the data was stored on the IBM 704 mainframe from the mid-50s, which had, I believe, 3 registers. No, 5 registers, and 3 of them were decrement registers. So back in the day, it was probably completely reasonable to call them the car and the cudder. But today, it's a bit strange. But the beauty of it is that these names actually compose. This is my absolute favorite part of them. So you had something like the cudder as a function in ancient Lisp, which is the car of the cudder, which is basically the second element of a list. The car would be the first element, the cudder would be the list without the first element, and the cudder would then be the second element. The cudder, this is actually the canonical pronunciation, is the car of the cudder, which will be the third element, and you could keep going. You usually had like up to at least 7 or 8 of these. And the other way around, you have the cudder of the cudder, which is the third element. The list without the first and the second elements. And the cudder would be dropping the first 3. It's a subtle difference. You have the cudder, which is the third element, and you have the cudder, which is the first 2 elements dropped. And so on. But nowadays, actually, I just prefer to call it the head and the tail, if you don't mind. I guess the easiest way to visualize this is sort of as a list. And the car is the head, and the cudder is the tail of the list. The head would be the first element, and the tail would be all the other elements of the snake, sort of. Bonus points if you can name this Pokemon. Did somebody say Dratini? Excellent. I respect your knowledge of the Pokemon. But actually, as I mentioned earlier, this is actually a tree in a way. Because what the consel actually is a straightforward way to represent a binary tree. It's just that it's really, really unbalanced. So if this is a consel, what I'm going to show you is a list of the elements 1, 2, and 3. So I got me a consel, I open it, and on the left hand, you see the value 1. On the right hand, there's a pointer to another consel. If I open that, you got the value 2. And there's another consel on the right. So this is the car, and this is the cudder, right? Can't see anything. Oh. Yeah, I forgot to mirror that one. Right. Thanks for letting me know. Once again, then, left hand, value 1. Right hand is a pointer to another consel, where the left hand is the value 2, and a pointer to the final consel, which has the value 3, and no pointer, signifying this is the end of the list. So this is a binary tree. It's really unbalanced. But it totally works as a cons list. And so it has one interesting performance property. Now, mostly operations on this are going to be really inefficient. But there's one operation that's incredibly fast, and that is pushing to the front or popping from the front. Popping from the front is basically just looking at the car of the console that is the start of the list. And pushing to the front is basically creating a new console that points to the previous list. And what you'll note then is that when you create a new list by pushing to the front, by creating a new console, what you're doing is you're sharing structure with the previous list. The previous list still exists. Given that consoles don't ever change their values, it's totally safe to take one list, add a console to the front, and just point to the rest of the list. And both of those lists are always going to stay the same. And it's, well, I mean, there's one allocation, but otherwise it's like blindingly fast to operate on the front of the list. But you'll notice that anything other than the front of the list is going to take a bit more work. See if we can get back to this. OK. And this is where we should actually start talking about complexity. Because we need some terminology to be able to talk about the complexity of these operations. Like, we want to describe how pushing to the front of the console is actually really fast, and pushing to the back of it is horrendously slow. And so I'm going to teach you big Onotation. Big Onotation is, well, it's a way of describing complexity of operations on data structures. And we have basically three fundamental terms in this. We've got the constant time case, which is described as O1. The O with the one in parentheses, which means that it doesn't matter how big the data structure is, you're still going to do the exact same amount of work every time you perform an operation that runs in constant time. And we've got linear time, which we write as ON, which means that for each element in the data structure, you're going to have to do a certain amount of work for that element. And this doesn't necessarily mean that you have to go through every element, but it means that you have to go through them in sequence, basically. And then there's logarithmic time, which we write as O log n, which means the number of operations you have to do are logarithmic on the size of the data structure, which means basically if you got one element, you do one operation. If you got two elements, you do two operations. If you got four elements, you do three operations. If you've got 8 elements, you do 4 operations, and so on. An example of this would be a well-balanced tree, which we will look at in a moment. And then you've got a couple of others. Click is broken again. There we go. You've got polynomial time, which you write as O(n) squared or O(n) cubed or any constant power of n, which is just really bad. If you've got an operation that takes this much time, you probably don't want to be using it. And then you've got exponential time, which is an absolute catastrophe. That would be when the amount of elements in your list is the power. That just goes to infinity pretty quickly in practice. But fortunately, we don't see a lot of those. We see basically ON, O log n, and ON. Constant time, logarithmic time, and linear time. Those are the ones that we tend to care about. There's one more, though. There's ON log n that you might see, which is basically linear times logarithmic time. You'd see this in a good sorting algorithm. Some sorting algorithms are very bad and would run in polynomial time. Don't use those. Nowadays, the worst case for a sorting algorithm should be ON log n. And the best case should be more like ON, linear time. But we're not going to look at sorting algorithms today. That would be excessive. So let's put this to practice. Shall we try and name the complexity for operations on arrays? So push to front. Anyone care to guess? ON. Push to back. ON. You got to, I mean, given that your array can't grow, you're going to have to basically copy everything every time you want to change it. Same with concatenation, that would be on plus m, the length of the first one and the length of the second one. Lookup, though, is extremely fast, because you just basically find the right index, the right memory address offset from the start. And for const lists, push to front. 01, that's the fast one in the case of the const list. Push to back is on. Concatenate is on, not on plus m, because you can reuse the right-hand list in this case. Lookup, on, because you actually have to start at the start of the list and walk your way through until you get to the right index. So none of these are particularly great. An optimization we can apply is amortization, which means basically spreading the cost over several operations. The word, I think, comes from banks lending money, so that you can do a down payment over a longer period. But in our case, it means that complexity is usually one thing, but sometimes will go a lot slower. So a trick we can do to the array is to pre-allocate memory, in case we want to grow it, and basically keep an extra value around tracking the current length of the array. So this is my drawing of that. This would be an array of length 3, but capacity 6. So the last 3 elements in the array aren't actually assigned to anything. So if you want to push to the back of this, that would be very fast, as long as there's capacity. So we can push 3 elements here, and it's going to be really fast. It's going to be 01, essentially. But once you hit the capacity of the array, you're going to have to relocate the entire thing, and that's on. So that's an amortized 01. Basically, push to front is at on, because you'll have to shift all the values. But push to back is now 01 most of the time, and I use that asterisk. This is my personal notation, not accepted computer science, to denote that this is amortized. So it's 01 most of the time, sometimes it's 01. Now let's talk about trees. I'm running out of time, good God I am. Okay, trees, very quickly. This is a binary tree. This is a binary search tree. The idea is that I've put numbers on each node. Think of the number as the key, and you could store a value next to it. So if you want to look up, say, the key 11, what would you do? You'd start at the top. The top is the one you got access to. The top is 8. And the thing with this binary search tree is that the keys are ordered. So you know that the key 11 is larger than 8, which means you go down the right-hand path looking for it. You get to 12. 12 is larger than 11. That means we go down the left-hand side. 10 is less than 11, which means right-hand side. And indeed, there is the 11. Now, compared to const list, what happened here? We basically saved us having to go through the entire list until we found the 11, because we could do these quick comparisons. What was the running time here? That was a log n, particularly a log 2n, meaning that basically we have a branching factor of 2 on the tree. So that's an optimization right there. Insert comes to the same thing, but it might not be entirely obvious how this could be a persistent data structure. Basically, for insertion into a mutable data structure, you just find the right node and then update the value right there. But so say you want to update the 3 here. How do we do this persistently and with structural sharing? Well, because there are so many nodes, mostly we just have to copy the nodes that we change. So we still have to find the path down to the node that we want to update, the 3. And what we do then is we start at the root of the tree. We make a copy of the 4 that points to the right-hand side of the tree unchanged. We don't have to copy that, we just pass the pointer along. And then we go down to the 2, we also have to update that, but we can just keep a pointer to the 1 unchanged. And we also have to make a new copy of the 3 that actually incorporates the change that we want to make. So we are basically able to copy only the path down to the nodes that we change, and we can keep the rest of the tree. That isn't quite as efficient as just pushing to the front of a cons list, but it's still pretty good, especially if it's a very large tree. So can we find ways to make tree lookup even faster? Well, the obvious thing to do is basically just to increase the branching factor. Like, this is a btree of branching factor 4, which means that the nodes can be, I think, 2 to 4 in size. Might be 3 to 4. A btree is basically just a kind of search tree that isn't binary. It's of variable length. And it's got all these rules that I'm definitely not going to talk about today on how to balance the tree, because to preserve efficiency, to keep it log n, the tree will need to be balanced. And what we've done here is basically we've gone from log 2n to log kn, where k is the maximum size of each node, which in this case, as you can see, is 4. And in practice, we tend to go even higher. I think my implementation currently is a 32 or 64. I keep going back and forth between them, trying to figure out sort of the optimal size for this. And at that point, it becomes really fast. There are very few steps to actually get down to the right node. And insert, likewise, would be log kn. Now let's talk about trees. Oh, I'm slightly running out of time here, so I'm going to go through this very quickly. But this is actually where it gets interesting. And horrifying, because I said trees. It's spelled tries, right? It's pronounced trees. So this is basically just a radix or prefix-based search tree. And a perfect example of how naming is actually the hardest problem in computer science. And sometimes we just get it really wrong. Because, so tree is short for retrieval, as in a retrieval tree, T-R-E-E tree. And for some reason, they decided to pick this very ambiguous to spell word and decide to pronounce it exactly like the thing that it is essentially made of, a tree, T-R-E-E tree. And it's, I'm so frustrated with this. So a lot of people are taken to just pronouncing it as tries, or a try, rather than the canonical pronunciation of tree. Because sometimes its inventors get things wrong, like GIF. If I'm going to be controversial here, like GIF, nobody says GIF, that's ridiculous. It's pronounced GIF. And it should probably also be pronounced try, so I'll try and keep doing that. So a prefix try would look something like this. This is just a diagram I picked off Wikipedia last night. The idea here is this is a string-based lookup tree. So suppose you want to look up the value for the key T down there, T-E-A-T. You'll notice the number 3 below it there. That's the thing we're looking for. And we know that the keys are strings. So basically, we start at the first letter, T, and we find the T at the top level. There. There's the T node, and then the next letter is E, and indeed we have an E path down here. And the next letter is A, and we found the T key quite efficiently. And the value is 3, and so we've succeeded in looking it up. The next thing I want to introduce you to is this fellow here, Phil Bagwell, who basically, I think, invented all the very cool modern data structures that are built on tries. And also this fellow here, Rich Hickey, who built upon the work of Bagwell to create this data structure here, which is the persistent vector from closure. It's called, the thing is, Rich never actually gave it a proper name, but it's been called a bitmap vector tree, I think, by Daniel Spivak. It's nowadays just referred to as a vector tree. Sorry, not a tree. This is horribly complicated. One poor naming decision. And the idea here is basically it's, well, you can see it's a tree, but the trick here is you get the index that you want to look up, which is an integer. Suppose you want to look up the last element in this list. So you can think of the bottom level here as essentially an array, except it's been chunked up. And it's got levels above it that enable you to find it. And so if you want to look up the key 20, what you do is you convert it to binary. That's 10100. And as this has a branching factor of 4, that means 2 bits to represent 4 values. So you chop it up, essentially. At the lowest level, it's index 0, 00. At level 1, it's index 01. That's 1. And at the top level, it's index 1. So basically, we look up. This is index 1 at the top level. And it was index 1 at the next level. And it was index 0 in the node you find here. And you found your 20 very efficiently. Likewise, I've put the 14 up here. That would be 0, and then number 3, and there's your 14, number 2 there. Now, the reason it's done like this, of course, is that this is basically, it's intended to work like an array, but it also needs to be efficient to copy it, because this is supposed to be a persistent data structure. So we're basically using the same strategy as with the binary tree. We just copy the paths down to the element that you want to change. So performance here, very quickly, lookup becomes O log kn. And the branching factor in closure is 32, which means O log 32n, which means, I think, at worst, you will have 5 or 6 steps if your vector is really, really large. And pushing and popping to the back, essentially the same performance. But popping to front is still slow. Now, really running out of time, so I'm just going to very briefly try and explain the optimization that was done here. Basically, he put a tail on it, so that you only ever add full chunks to the tree, and you keep a pointer to just a tail, just an array that is pre-allocated to the size of each chunk. And when it's full, you move it into the tree. Or when it's empty, you move one chunk out of the tree. And that actually gets us a motorized O1 for the push pop back. And there's a further optimization you could do if you want to fix the front as well, which is you can add a new level to the tree at the top, which means basically your entire array is shifted to the right by basically the size of the level. And so if you keep a floating origin, so basically saying that index 0 is now index 1024 or something like that, you actually can efficiently allocate space in the front. And you can use the same trick there and so on. And I am just going to skip over this now. I am seriously running out of time. There's the other data structure in Closure, which is the hash array map trie, which is a key value store, which is basically the same principle as the vector trie, but it uses the hashed value instead of the index and some trickery so that the tree can be sparse. And the performance of that is similar. But right at the end, I want to talk about the perfect data structure, because I think between the btree and the hash array mapped trie, we found a performance as good as it gets for key value stores. But I'm not quite happy with the performance of sequences, because there's the matter of concatenation. And everything we've looked at so far is concatenating in linear time. So we got some tricks. We got casted number lists from Okazaki. And that gets us O1 concatenation, but it completely ruins lookup at ON. We got the new cool thing, finger trees from Haskell, which I've actually tried to implement in Rust, and Rust's type system just can't handle it, which is unfortunate. But I think you could do it easily in a language like Clojure with no type system to worry about, which gets us similar performance, but still lookup is ON. And this is where relaxed radix balance trees comes in. Obviously, the last thing basically Phil Bagwell gifted to the world before he sadly passed away in 2012 is this thing, which is basically a hack on the vector trie that we saw earlier, but it's got lookup tables for, it allows nodes to have varying size, even if they're not at the end. And it's got this lookup table to quickly still let you actually discover where an index is in the tree. I'm not going to go into details about this. I'm just going to give you a paper to read if you happen to be interested right at the end. This gets us to, so this is the thing I'm trying to implement now in my own library. RRB trees gets us pretty much O log K and performance across the board, which is even an improvement on basic arrays, if you could get the implementation efficient enough. So that's pretty much it. I am so terribly out of time. This is the reading list. I'm going to get your photo. I'm going to put it back up afterwards, so you can make your notes. I just want to mention implementations of these data structures in different languages. You got Immutable.js in JavaScript. You got bifurcal in Java, though the author might be mad at me for plugging it because it's apparently very alpha. I don't believe him. It's too good to make mistakes. There's Immer for C++, which is very powerful and probably the fastest currently. And there's my own Im thing for Rust. And that was it. Thank you so much. The easiest thing to do if you want to get to the reading list is to note down the URL that you just saw, which actually gets you these slides. And the reading list is right at the end. Do we do questions?
Perfect. Thank you very much, Bodil. We have one question in the message wall. Have you ever felt the need for garbage collection when implementing persistent data structures in Rust?
Yeah. Oh, yeah, I could go on for a long time about this, but we have got 2 minutes, so I won't. Oh, absolutely. Persistent data structures and garbage collection go hand in hand. This is absolutely crucial. And the problem with Rust is it doesn't actually have garbage collection. It's just got these linear types that would sort of know when to clean things up for you, except when you're sharing structure like you do in persistent data structures, that's no longer an option. Fortunately, Rust provides simple reference counting, which in most cases is good enough. And it allows for some really cool hacks, because when you can actually access the reference counter, it means that you could basically be writing an implementation of a data structure that is mutable and still able to know when it needs to copy itself in a proper persistent fashion. Because you know whether you have whether you are actually sharing structure as a particular node. It's actually really powerful. The only problem is, of course, it's just reference counting and not real garbage collection. So if you've got cycles in your data structures, that's a memory leak. But I think there's a good reason why you tend to see these data structures popularized, mostly in languages like, say, Scala and Clojure, that actually have good garbage collection. Because you absolutely need some sort of garbage collection to make this work.
Perfect, thank you. Any more questions from the audience?
Yeah, so you talked about the complexity of the algorithms, but I think you talked mostly about the runtime, but what about the memory complexity? Is there any difference between the different trees?
Well, yes. So basically, they are pretty similar. And the RRB tree is perhaps the one where you might need to allocate some extra space for that size table. But in practice, I think mostly, obviously nothing will beat an array. But mostly you are storing arrays of pointers to the next level of the tree and the actual values, and that's pretty much it. They can be, at I guess worst case, you're going to see like 2.5 times an array, maybe. It's not too bad. Of course, it depends on the chunk size, because say a persistent vector will be at minimum 32 items allocated. But mostly like pretty good.
Great. Even more questions?
Guess that was it.
In that case, I would say a very big thank you for Bodil. Our next talk is at 12 sharp. It's Aaron Cruz on the professional crypto mining tech stack. But now let's give a big hand for Bodil. Thank you very much.